Hello, I'm Guan Qun, and I'm a PhD candidate at Stevens Institute of Technology. I'm presenting TestAug, a framework for augmenting capability-based NLP tests. We have seen many successful NLP applications like Siri and Alexa in the past decade. They have greatly influenced our lives due to their ability of analyzing sentiments and translating between languages. The conventional approach for the model developer to know whether the model is good enough is through the lens of the Hilda mechanism. That is, we train different models on the training sets and find the best one on the test set with an aggregated metric, such as accuracy and effort score. Using accuracy and effort score to evaluate a machine learning model seems natural, and it is actually a widely accepted practice. However, they could give us inaccurate estimate of system performance because of the annotation artifacts such as bias during dataset curation and unintentional shortcuts via labeling data. This gives the user a difficult time to choose which model to use. For developers, an aggregated score cannot help them with identifying the model failures and fixing these failures. To this end, a previous work named Checklist proposed behavior testing to solve the above challenges. Checklists analyze the linguistic capabilities related to the task at hand. The developer then create templates and fill these templates with a predefined list of words. For example, to test a classifier's ability to detect sentiments of the following rhetorical questions, two templates are crafted by developers. We could create a list of concrete test cases by filling these slots with a predefined list of words. Following this approach, many commercial APIs have been shown to have severe bugs, even though they have been stress tested before deployment. However, since the previous approach relies on templates, this brings up two issues. The first issue is the low scalability because writing templates requires expertise. A perhaps more severe issue is the low linguistic diversity, as only words in the predefined slots change. For example, in this table, only the names of people are different across different test cases. In this work, we try to address the previous work's limitations in linguistic diversity and scalability. This requires us to alleviate the reliance on the templates. Also, we need to reduce the manual efforts involved in this process. Recently, GPT-3 has shown the potential to generate tests by following instructions. We propose to use GPT-3 to generate test cases for augmenting existing template-based test suites. This is in contrast to the previous approach to filling out templates. At the same time, this approach requires little manual efforts. We use the description of linguistic capability as a prompt. They are color blue in this example. We sample 3 template-based test cases as input for GPT-3. They are color green in the example. The GPT-3 generates yellow text as a response. Note that here the format matters. Here the bullets and the brackets indicate the boundaries of different sentences. Even though we have tried various ways to ensure the output is valid, there is still a possibility that the GPT-3 generates invalid outputs. These invalid cases could either violate the description or expected label. For example, the sentence "food isn't great" is not negative, and "I wasn't expecting much" is not neutral. This violates the description "I saw something was negative, but it was neutral." And the sentence "Joe is at the party" contradicts the first sentence "Joe isn't at the party." This violates the expected label. To address GPT-3's invalid output problem, we propose to train a validity checker to automatically filter out invalid cases. We use a validity threshold of 90% to decide whether to train a checker for a particular description. The checker is done on an independent set of samples collected and annotated ahead of time. We find that after our validity checkers have been trained, they all have accuracy about 90%, as is shown as orange bars. This significantly improves unchecked validity rate, as are shown as blue bars. With the help of these validity checkers, we could automatically generate valid test cases at scale. We also found that newly generated test cases could be converted to new templates following a simple approach. That is, converting the reappeared words into new slots. By expanding sentences into new templates, we can expand the set of available templates. This makes it possible to generate even more test cases. For example, the template lists words like seat and service give us "no one enjoys that seat." If GPT-3 outputs "this is not an easy service to appreciate," as the word "service" reappears, we create a new template. "This is not an AR slot to appreciate." This table shows that this template expansion process is possible for numerous tasks. A good test suite should have a good bug detection ability and good linguistic diversity. Let's first look at linguistic diversity. One measure we use is cell BLEU 4, the average pairwise BLEU score within a corpus of up to 4 grams. Here, a smaller value of the cell BLEU 4 indicates more linguistic diversity. Another measure we use is the number of unique dependency passes. A larger number means a more complicated sentence structure and thus more linguistic diversity. Let's now look at another desired attribute of a test suite, bug detection ability. As there is no previous metric to compare to test suites in terms of bug detection ability, we propose a new metric. We first sample the union of all test suites as a test set. The set differences of this test set with all test suites give us training sets. If there are n test suites, then we will have n training sets and 1 test set. We then fine-tune the model with different training sets and evaluate the model on the same test set. This gives us n performance metrics, which correspond to each of the test suites. Then, whichever test suite gives us a smaller error rate is better. This is because more bugs are patched with fine-tuning. We compare our TestAug system with the previous checklist system on 3 tasks: sentiment classification, paraphrase detection, and natural language inference. Each of the tasks involves multiple models. We then compare the test suites in terms of linguistic diversity, bug detection ability, and how much manual effort are saved with our framework. Compared with checklist test suites, our test suites have consistently lower BLEU 4 scores across 3 tasks, and consistently more unique dependency passes across 3 tasks. Therefore, our test suites are more linguistically diverse. Originally, the error rates on the standard test set were low, but when there's a new test set, the error rates at least doubled. When comparing test suites generating following 2 approaches, our test suites give lower error rates after patching. Therefore, our test suites could detect more bugs. Finally, we evaluate the manual effort saved with our framework. We use a number of new templates for this evaluation. Specifically, we create new slots for reappearing content words, including verbs, nouns, and adjectives in newly generated sentences, and filter those invalid ones with our classifier. We then use a number of new templates as a proxy to evaluate the amount of manual efforts. We could save at least 98% of the manual efforts. In summary, we propose a novel framework TestAug to generate capability-based NLP tests based on GPT-3. Our framework outperforms prior art in 3 critical aspects: bug detection ability, linguistic diversity, and manual effort reduction. Our code to generate test suites and our generated test suites are available by scanning this QR code or visiting this URL. Thank you for your time. I look forward to seeing you in the poster session.